Good morning, everybody. Right now is April 20. We have the week 5 session 2 on programming language. And in this week, we are going to discuss the chapter 8, the composite data type. Before I get started in the composite data type, I would like to first say sorry for the previous session, week 5, session 1, because the Blackboard system is under maintenance for a while, so the recording is a little bit late. Sorry for the call. And we actually got slowed down. And the second thing I would like to discuss is this session, I'm going to divide it into two halves. So today I'm going to record the first half, and then next.
Hello, this is Republic Services, your garbage and recycling provider. We are contacting you today as a courtesy.
Sorry for the call. And this week I'm going to divide this session 5 into this session 2 into two halves, because this chapter 8 is actually too big. Totally, we have around 160 slices, and I estimated it can be done within one session. So I will divide it into two sessions, and today I'm going to cover about 80 slices before the pointer, and anything after pointer, including the pointer section, will be discussed tomorrow at the same time, 9 o'clock Pacific time, and then 11 o'clock Central time. And I still have not finished all of the homework grading yet, because this week I focus more on providing the material for the generic programming part. And let's get started for this chapter 8 composite data type. Some of the slices you may not be able to see it on the Blackboard system yet. I have not uploaded because I updated this file, but I have not uploaded. But I will do it right after this session. And also, this chapter 8 is related to chapter 3, 7, and 8. And I'm sorry that this year it's the first year we teach this textbook, and next year I'm going to group this together as one part. So probably we would do this. We would do chapter 2, 3, 4, next 2, 3, 4, 5 for the compiler system, and then 3, 8, 7, 8 for the data, and then we will do 6, 9, and 10, 13 for the control. That would be a more logical way of doing things. But this year actually, this semester actually is the first time I try it, so the order is not as what I predicted. And in this chapter 3, 7, and 8, in chapter 3 we talk about the scope, binding, naming, those kind of things related to the relationship of the memory and the variable name, the ID. So it's suitable for the Lex or EX environment to deal with those binding part. And chapter 7, we talk about the scope and type checking. So actually that is related to determination of the type. And we know that the type is related to the declaration of the syntax tree. So some algorithm like backpropagation actually is to determine the attribute in attribute grammar. So those attributes like type actually can be determined by backpropagation algorithm. So that's also related to the compiler part, but actually it's not listed over there, and it's not going into that detail about the compiler design. And this chapter A is more focused on the composite data type, about the memory allocation of the data types, and also looking at the data types from a programmer point of view. So let's get started for this chapter 8. First, let's look at the overview for composite data types. For composite data type, we have the record, union, array, strings, sometimes array, and sometimes it's object depending on the language. And we have set, dictionary, or sometimes call it map, and then pointer, list, and file. I believe we have this chart, this slides in chapter 7. And right here, this one, the data structure, this is from the abstract point of view. So this is called a very simple abstract data type tree. So we can look at the abstract data type as linear or nonlinear, but this is for data structure. Something that is only has a data primitive data type or some certain data type, we call it atomic data type. That means that there is no organization about the data. So each data is an individual unit. And right here, this data structure actually including the organization of the data. That means that data are organized in a certain composite way. And that's what we are talking about right here. So composite data type actually is related to data structure, but there is a certain difference. Data structure is a conceptual term. So right here, we are talking about the conceptual idea of what data organization is, or we call it data structure. And this data structure can be implemented by composite data types. But composite data type is a data, the language structure for the data organization, but it may not cover all of the data structures that we have. And some of the data structure we have, like this linear data structure, array, linked list, stack, or queue. These actually are in some of the design framework or the SDK, or in some language is actually can even be the part of the language. And that is the linear data structure. And for nonlinear, like tree, table, set, or graph. Some are also in the data collection or API, but some actually will need to have the custom designed data structure. And these are the conceptual or abstract data structure. And it may or may not be supported by the language. But that's the optimal goal we want to have, is actually design some data structure to support the algorithm. So from computing or algorithm point of view, data structure is the optimal goal that we would like to pursue to help to solve the problem. So problem solving is still number one, and we find the data structure and algorithm to solve the problem. And the language actually should support this data structure and the algorithm. So we find the appropriate language with enough enough data type, composite data type to support the data structure that we need. And it all depends on what type of application we have. So right here, this one is the abstract data types. And abstract data type is to support the data structure. And we may have stack, queue, set, and map. And stack can be even be classified as, sometimes you can have a vector, and vector sometimes is can implement stack, or stack implement vector. And sometimes you have other way to implement stack. And you have queue, you have linked list, priority queue, and heap. And you have set, you have hash set or tree set. That depends on your implementation. In Java language, actually set has the hash set, tree set, and also has the linked list set. And also we may have map, and we have hash map and tree map. These are called abstract data types. An abstract data type is to support a data structure, but may or may not be complete enough. And abstract data type may or may not be in the language as well. Let's look at the first language, C language. C language data type have fundamental data type, or in Java we call it primitive data type. And they are also derived data type, and that including array and pointer. So the derived data type right here is actually much weaker than what we see in abstract data type in previous slides. So, and right here we also have the user-defined data type that's only for record and the union, and record is called struct or structure. So C language actually provide very limited support for in the language itself for the derived data type and data structure, but it will require the programmer to do everything. So it provides a pointer and structure. Basically, these two data type are very powerful, and then you can customize design anything you need by using pointer and structure. Basically, using pointer and structure, you can build any object, and the object or module that you develop in C language can always implement all of the data structure that you need. So, but C is not an object-oriented programming language, so it doesn't have all of the it doesn't have all of the nature. It doesn't have all the support or classes available for the data collection that we need. C++ actually improve on that. So C++ also have the fundamental data type, or we call it atomic type. And in derived type, it also has this array pointer, but it includes functions. But in reality, actually in C, functions can also be passed, and it is actually called pointer to function. But pointer function name can be passed as a closure. And right here, the function we talk about in C++ is more related to the lambda expression, those lambda expression functions. Function as a pointer still be valid, and it also has a new data type called reference, and reference is the opposite of the pointer, and we discussed this before. And we also have the constant as a built-in data type for derived data type. But actually, the real new thing is the lambda expression and the references. And it also has the class that's new for C++, and the newer version of C++ also had the template that is actually to support a generic programming, and generic programming is an important feature for the future. And right here, it also had enumeration. Actually, is an old concept. So the real new one is actually the class, and enumeration actually is an old concept, not supported in C. I believe C should have this. Yeah, C has this, but actually C++ 11 has some update on the enumeration to allow it to be defined as a type of different more improvement. So this is what C++ is. So basically it adds lambda expression, reference, class, and the enhancement of the enumerations. Now we look at the JavaScript and the Python. These two are the scripting language. So in JavaScript, you actually just declare something as a var variable, and The original JavaScript don't have the object or class. But because of the need to operate the document object model and also window object model, so object is actually there to help to process the JavaScript, the computing. And actually, in early version of JavaScript, early version of JavaScript, when I started JavaScript, there is no idea of such thing as object. So what we did is we have a input form, and the input form will have some data, and we process those data field in JavaScript and then update on the form right away. So there is no such thing as DOM, as data object model. But later we have the data object model, and even recently we have those JSON, those different object notation, JavaScript, JSON, JavaScript object notation. Yeah, those kind of the data structure. And those data structure even used to replace XML. In the old days when we do it, XML is similar to HTML. The language structure is similar to HTML, so it can be embedded into HTML. But nowadays, all the XML will be replaced by JSON or some other format like JSON. And that is the JavaScript. And Python is pure object language that I talk about it. So the data structure is actually very simple. It just gives you basic variable, and those number and the string actually have no data type. And we have basically most commonly used is list. And the list in Python is actually different from the list in Java or the array in Java. Actually, the list itself is an object. So you can do a lot of list operation as Java as object-oriented programming. And we have dictionary set and tuples. And these are the basic data type for Python. And actually, if you don't use NumPy or SciPy, actually there is no array at all, no array in Python basic language. And you have to use the NumPy to get the array definition to the array, something like that. And Python, in some sense, is very close, it's closer to Lisp or ML type of language that is more like a dynamic language, and it's actually interpreter based. And so it's more like a functional language. And that's quite good. That's actually a good feature for Python. So it's suitable for those machine learning type of job because of its relationship with the list and its easiness to operate and write code. But advanced Python programming actually is not that easy. They have a lot of detailed things and hidden and not easy to find a document to support it. And for Java, it's also a C family language. And as we see, Java, the primitive type part is similar and smaller than C language, but easier to use. For the composite side, it has its unique thing called interface. Many languages don't have the interface, but this interface actually is, you should think about it, the interface abstract class and the enum, enumeration, or I call it enum. This data type actually are classes, specialized classes. Even the test unit, JUnit's test class also is a specialized class. So Java actually allow many kind of different specialized class. And in Eclipse or some system, you can even initiate a class just by using the template. And generic programming after 2004 in the newer version of the Java 4, 5 and beyond actually make the Java composite data type more powerful. So that's why we have the special tutorial on that. And structured data type, we have array, and that is the single data type we have in Java to support that. And in terms of the record, something that Java doesn't have that. Java just have class, and class is actually good enough to replace the records and structure. Ada is for defense and more reliable or secure computing. And actually, Ada's numerical type is more complicated. So it has a big real scalar data type for discrete computing and the real computing because it is used for defense. So the numerical computation is a big part for Ada. And also Ada is specialized in more secure computing environment. So it has a special data type called task. And task actually is also I should say it's similar to class or thread that we will discuss in chapter 13 for Java. It's more like that. And so actually it supports concurrent programming, and it's one of the early languages that support concurrent programming. And actually they use that task as one of their composite data type. And task look like it's a program structure, but it's put into the composite data type. So you should look at task in Ada like a class or like a struct or like a program control unit, a specialized class for Ada data type. So actually this is the Ada's data types. Now let's look at the lecture 1 on records or structure or units. First, we will look at the structure or records. Records actually is just a collection of data fields. So for example, like when we have a single atomic data type, like we have a double value. So the double value actually can only use for 1D data or one tuple data. Say I have a number or my money or something like that. And record is useful when we need to have a group or a collection of data field together. For example, I have a 2D coordinate, or I have a location, or I have a point, or I have 3D point. That I need to have the double X, double Y, double Z as my coordinate. And those kind of things is called a vector or sometimes called a point coordinate. Then you cannot have, you can actually use 2 integer or 2 double to represent that, but that is not very efficient. So we can have a record or structure for that purpose, and then we also can use the type define to allow that type to be used over and over again. So usually layout contiguously and possibly might have possible holes for alignment reasons. Smart compiler may rearrange field to minimize the hole. Implementation problems are caused by record maintaining dynamic arrays. So here, point out a few implementation issues for record. But before we dive into these implementation issues, we would first need to know the records actually have a few things. In numerical computation, we actually use the record for those vector polar system, for example, like angle and radius. in polar system, or we use that for coordinate. And on the data processing side, the records actually is a data unit in data structure. So we may have the records for students record, including the student ID, student name, students ages, students GPA, students gender and age, those kind of information in one record. So record is a collection of data, and record may have different data field, and record's data field can be homogeneous or heterogeneous. For the homogeneous data field, we may have two integers in the same record, or two double value in the same record. But the heterogeneous one, like student record, that may have a string for student name, might have a number for student ID, might have a double value for the student average GPA, may have another string or even a file to store the ages or some essay that the student have completed. So those kind of record actually is heterogeneous data type. And so record is a collection of data. It can be homogeneous or heterogeneous. So we won't dive into here in these slides. We'll go over. And then we will also have the variants. And variants, we call it unions. And it actually have the overlaid space and could cause problem for type checking, because when you check the type, the unions actually have two, three different data type in sharing the same space. And unions lack of tick means you don't know what is there. So you actually don't know what is inside the union, whether it's type 1 or type 2. We don't know. So ability to change tag and then access the data field hardly better, and can make the field uninitialized when tag changed, and can require assignment for entire variant as in Ada. So actually, the record is hard to implement and actually hard to explain. So in many language, if not C or C++, actually, union is a very rare thing data structure. Usually people just would rather to use different record to represent it. Now let's look at let's stop here. Let's look at let me try to bring up not this one. Let me bring up the discussion. Okay, let me try to find this one. Let's look at this calculator 3. The union's main application is right here. Remember that we have the output from the YY-lex in the lexical analyzer or scanner generator, the lex or flex program, the flex program. For the calculator 3, we actually it allows the YY-lex to generate three data types. One is integer value. When you have an integer, we return as integer. And when you have the simple table index, then we return a character that is actually 8 bits. I'm sorry, 8-bit 256 entry of the symbol table, and this is only a bit or 1 byte, and then you have the no pointer to the syntax tree. So this three data field is sharing one space, and it is returned as a YYL val or YYL value by by the YYNext program. So YYNext program, every time it will return this YYLVAR value back to the parser. And this value actually sharing one space. And this is a good application for for union. And actually union, normally they are used in C language. They are used in some kind of the application like this. You have an input string, you have an output string from certain data source. Like in this case, is from the scanner, and it is actually provide a token string. So token string is one string, and that token string provide you this YYLVAR value every time. When there is a new token, they will provide you this YYLVAR. So YYLVAR itself is one string, and this string has different data format, and we use union to accomplish that. So union, to be short, the main application is in this kind of the data streams that may have different format and even of different type and different lengths. And we can use like this union to be input or output record. It's kind of sort of a record, but they are sharing the same space. They can have different format at different time. And you write that into an output file or read that into an input file as the interface for the data stream. Now let's go back to our slides. So that's our main application. That's our main application for the unions. So right here, I show you the syntax for record or structure. Let's look at the Pascal first, even though Pascal is not commonly used right now. So we have a type that's 2 characters. So 2 character is a packed. We will explain what's packed later. It's a packed array of 2 characters with the index 1 and 2. And so there is 2 characters, and this 2 character was put into name. Okay, so this put into name. And so there's a name field, data field, there's an atomic number, that's integer, there's an atomic weight, that's real, there's a metallic Boolean variable. So this actually is the element that you see in the periodical table, that you have 2 characters. So for copper is Cu, for gold is actually Au, something like that. You have H as hydrogen, you have O as oxygen, you have neon, Ne as neon, something like that. So actually this is the element used for periodical table, and you have the name, atomic number, and the weight. And this is the Pascal way of doing it, and this is C way of doing it. So Pascal has a type declaration. So let's declare a type. So this actually is not a real record. It's only a type. So this type is put in here. So this name is of this type. And this, again, the element is a record or a type. So this one is actually another type. So you can declare some other elements somewhere else. This one structured element is actually a record. It's not a type definition. And this record has also 4 fields. It has a name of the 2 character array, and then it has integer double for weight and Boolean value for metallic. So to access a data field, actually we can this one, you can put an element that's copper. So this one is in C format. So actually this is a structure. You use this to declare a structure called copper. And in copper, you have define this constant double, that is this 6.2022 to the power 23. It's called Avogadro number, that give you the definition of how many atoms in 1 mole of the elements. And okay, I don't know whether you guys know this or not. So that's the Avogadro number. And then you have the copper name. That's the first letter, 0. That's the first letter. That's C. And the second letter is U. So Cu is the element name or the Chou notation for copper. And then we have the atoms. That's equals mass divided by atomic weight times the Avogadro number. So actually, mass divided by atomic weight. This will tell you how many more is there times the Avogadro number. That will give you how many atoms are over there. So this is the calculation for the number of atoms for this amount of mass. Syntax for record, we have OR. OR is somewhere we dig out these elements. So this OR would have a name, 30 a string or name of the 30 array, a 30 element array of characters. And there is a certain structure, and this structure is actually an element, but we actually put this field as element yield. So we put the record name over here. This become a data field name for this structure OR. So in structure OR, we have 2 data fields. One is the name, the other one is the element yield. That is your field name. So the field name is name, and the element yield that's in this OR structure. And there is no type name for structure right here, and because it's not needed, you just need a field name. And you can also use the previous. You can also use the previous element type. This element definition use the type name over here, but this actually is not type defined. This is just a record type defined, and we actually can put that element name over here. So this one is actually calling that structure. So give you a structure like this, and the data field name is the element yield. Name and yield and an element yield. These 2 data field is actually build up this OR structure type. So this is the alternative way of saying structure in C language. Record structure, if we do not pack the data, this element should look like this. So you have the name, that's a character type. You put actually 2 bytes over there. And atomic weight, that's integer type, that take 4 bytes. And double take 8 bytes. And then metallic, that's a boolean, that actually take up actually 1 byte. So this is a likely layout in memory for object on a 32-bit machine. So why we use 32-bit is because of the machine or the register size. So for compiler, they want to save time every time they load 4 bytes into the register. Excuse me. So for the unallocated memory, that is a waste. And those waste, we call it hole. So actually right here, we actually wasted 2 bytes, 3 bytes, we wasted 5 bytes. And each of the structure actually For the compiler, you would actually allocate 20 bytes, 4 by 1, 2, 3, 4, 5, 4 by 5, totally 20 bytes for one structure or one record. And the fields of a record are usually stored in adjacent location in memory. And right here, I would like to talk about the structure tag and the type define in C, C++. I personally prefer the type define. Okay, so type define is like if I would like to define a type, I would say type define structure and put a structure over here. And then this name song is the type. So this song is actually a data type. So if I did a location data type and I have integer x and integer y as the 2D coordinate, I would put here as point or something like that. And every time if I need to have a point 1, point 2, point 3, I put a point and declare some structure or record as point 1, point 2. This is the type definition. This is easier. So you can put song 1, song 2 of different lengths and year recorded as two tuple structure using the type define. This is the type define in C, C++. And structure tag, that's the different thing. One of the peculiarity of the C-type system is the struct tag are not exactly type name. So struct tag, now you see struct tag, you need to be careful of this. This is called a struct tag. Struct tag itself are not exactly type name. In example 8.1, the name of the type is two-word phrase structure element. So structure element is a struct tag. We use this name to declare the EO element EO field. So element EO is a data field name for the second struct in example 8.3. To obtain one word name, we can use the type define. So struct element is a type name, and you can use type struct element, type define struct element as element T. Then this struct element will become, that is a type name, and then we define another type name called element T. Element T is actually the same type name as as element T. This is a little bit complicated. Let's go back. Let's go back here. So right here we have the data field called element yield and struct element. This is the type name. These two words is the type name. Okay. And in order to use one word type name, you can use type define struct element, that's the original type name, and you put element T over there as the type name. So next time you can use element T, element EO. Element EO is the field name. Element T is the type name. So what's this talking about? So struct tag and the type define name have separate namespace. So the set name can be used in each. So I personally prefer this type define one. It's easier to use. C++ eliminated this idiosyncrasy by allowing the struct tag to be used as type name without struct prefix. So in C++, this struct is removed. You can actually directly use the element. So element in C++ become a type name. So by default, you actually define struct element, something like that. So that's actually what improved by C++. In effect, it perform the type define implicitly. That's what I say. You actually perform type define struct element. This. So that is what the struct tag and type define in C, C++. So now let's look at the nested record as value. So right here we have one structure in C, and we have one structure in Java. So this structure in C, we have the structure T, and structure T has J and K. Structure S has one data field called I, another data field called N. So this N has N.J and N.K. That is actually structure T type. So actually that is what we have. So in C language, we declare one structure S of S1, one structure S of S2, and S1.N.J equals 0, S2 equals S1. When we have this S2 equals S1, we are copying the whole structure to S2. So S1 or S2 actually in C language, they are considered as a primitive like. The primitive like, I'm talking about the Java language term. It's primitive type. When you do copy using the assignment, it actually copy the whole thing over. It is not like in Java's case that is actually copying the address or reference. So be careful about this statement. And after the copy, you should have this S2.N.J equals 0, and then you assign the S2.N.J equals 7. So when you print out the S1.N.J, it is still 0 because this S2.N.J that get updated by 7 is actually a separate or different copy. But and the memory is laid out like this. When you declare the S structure, you have one data field I and one data field N, and N has two tuples in there. So your memory is organized like this. In Java's case, it's different. You declare a class that had two data fields J and K. You declare a class S that has two data fields I and N. And N is actually a reference data type. So N actually will point into T object, one T object N, and that is the J and K data field. So when we initiate S1, that is one of the S data type, then we need to initiate an N, a T type, and then assign this T object to hook up with this reference data type. That's what Java usually need to do. After that, you actually assign the address of or reference of S1 to S2. So S2 is pointing to the same data structure as S1, and S2's N.J will be this update to 7. So it actually already update whatever it is in S1. And what is in S1? S1, no tell, right? But in C, you have the initialization of the S1, of the N1. In Java, if you do not actually assign anything in there, the default value when the class, when the object is constructed without any assignment, that will set all of the instant variable to 0. So instant variable of the primitive data type, like integer double, was set to 0 or 0.0. For Boolean data type, it was set to false. For reference data type like this, N was set to null. So that null, it will be replaced by certain reference address that will build up this S2. So in this case, S1 and S2 are pointing to the same object, and the J update to 7. So when we print out S1.N.J, it will actually print out 7. And in this case, it will print out 0. Record type, layout or packed type. So in Ada, we have one pragma, that is a directive of the compiler, that will pack the element. Remember that we talked about the element type. In element type, actually, it's not packed. So with the compilation of the GCC, one use the attribute like this. You declare a structure, but the structure actually has an attribute of being packed, and then you define the same structure over here. And in ADA's syntax is to build into the language, and the GCC syntax is a GNU extension. So anyway, ADA's syntax can also be compiled by GCC, and then that will pack the element. The directive asks the compiler to optimize for space instead of speed. Compiler will implement a packed record without a hole. So let's look at the compilation. So that actually likely memory layout can be packed into like this. So you have name, and then you put a dummy number right here, and then weight right here. That's one way to pack it. And with this packing, we actually use only 15 bytes instead of 20. So that's how packing this actually save 25% of the memory for one record. And record, we have the assignment and comparison of record. We are talking about the operation that can be performed on the record. Most languages allow a value to be assigned to the entire record in a single operation. So this is actually the copy nature of using the ADA or the C double plus. Actually, is a direct copy of all the data field if they have the structure in a certain language. C double plus, many other language support through C double plus allow the programmer to define the later for individual record type. Assignment, but not equality testing. For small records, both copies and comparison can be performed inline on field by field basis. So basically, you can actually update by field. A block copy routine can take source address, destination address, length as argument, but the analogous of block compare routine will fail on record with different data in the host. So this block copy and block compare is actually sometimes can operate on more bigger data structures. And to solve the problem with the whole, one solution is to arrange all the whole to contain some predictable value. So actually that is a compiler issue to pre-fill some data over there. Okay, let's look at the next page. That is one way to pack it. And there are certain compilers, they will pack in different way. But after you pack it, there are some drawbacks. For example, like the previous packing will have a problem when you load into register. You may have to load with 2 instructions instead of 1. The previous one, when you use the 32-bit architecture, you may load in this in 1 instruction and load the lower part in another instruction that actually will create more instruction. It may not be saving. So we have different way of packing the record or structure, but this way also have its drawback. Actually, you need to operate this packing to be out of order. I mean, the metallic will move up. So you need to have a record to keep track of where your data goes. So a compromise is to sort the record field according to the size of their alignment constraints. All type alignment field might come first, followed by any hop word field, word aligned field, and double word aligned field. So basically try to fill in those fields. C double plus in order declared. So C double plus just keep to use the record type that we talk about, the unpacked format. But when packed directive is essentially a non-binding indication of the programmer's priority. Bit lengths on field declaration are a binding specification of assembly level layout. So basically, for programmer, they may not know it, but if you have the peg directive, some of the record may be pegged into some format according to the directive that received by the compiler. So arranging the record field to minimize hole by sorting field, this is one way to peg it. And actually, to be short, this kind of packing is done by compiler and not actually depend on the compiler writers. Now let's look at the union. Union is variant records, so it's kind of like record, but the only difference that the union has is they share the space. The overall size of this union would be the largest member. So in this case, double have 8 bytes. So the size of this union is actually 8 bytes. Exactly which bytes of D would be overlapped by I and B is an implementation dependent, and presumably influenced by the relative size of the types and their alignment constraint and the endianness of the hardware. So basically how they share the memory depend on the hardware, that's processor. So processor have little endian, have large, have big endian, so it's hard to say how will they share the memory in a record, in a union. And variant record, that's union type. Union have been used for two main reasons. So union are used to allow same set of bytes to be interpreted in different ways at different time in system programs. So that's what I say. It's usually used for some data stream, token stream, like those kind of application in I/O system. So it's used more commonly in in system program. And in fact, that's why it is commonly used in C++ language that is more used for system programming and the DSP type operation. Non-converting typecast can be used to implement heap management routine. Bits are not being reinterpreted. They are being used for independent purpose. Represent alternative set of field within a records. So in the records, you basically use for data that being interpreted in several ways, or you actually represent alternative set of fields within a record. So in the Week5S part is actually used for this second purpose. And the union, the first one, when it represented in the system program, usually is something like the permission word, RWX permission word or certain permission word that can be interpreted in different way. So actually it is, anyway, both ways are used mostly in system programs, and it is used for input-output buffer or different register words or the status words, those kind of flag or status register, temporary data, those kind of things in system programs. Traditional C union will occur when used for this purpose. A much cleaner syntax appear in the variant record of Pascal and its successor. So Pascal actually have more stronger records and variant records, which allow the programmer to specify that certain fields within a record should overlap in memory. Similar functionality were added to C11 and the C++11 in form of anonymous unions. And what should I say? Pascal is not actually surviving, and whenever the record is required for safer application, people use object-oriented programming. And for the traditional programming that use union, they still use the C union, and actually with these added union features. So basically, I should say the use of unions have been specialized in system programs. And for the non-system programs application for union and records, actually is people use more of the classes. And classes, you know, if there's a certain memory or data source that you need to read in different format, you can use different class as the format to access those files. So it's still not an issue in using class to have the different interpretation of data. You just need some sort of way to handle it. So right here, we are from the supplemental material of the textbook. We have this, and let's look at that textbook. Okay, this is the you can download it from, I believe it's the Start Here section, has this link. So that actually is actually this is the supplemental composite data type. Okay, so this one actually is the composite data type. So you should download it. So here we have the variant record union. And this part is missing from your textbook of the print copy. And you should download this file from the Start Here section. And right here, it has the more complicated element data type order. And that's returned to our slides. So that is the file we talk about. That you need to download a PDF file that's part of the textbook, but it's not in the printed copy. And this one, we have the same structure. So actually here, you can just use the element basic or something to put here. But right here, you still use all the data field. You have the element name, atomic number, atomic weight, and the metallic or natural occurring. It adds one more Boolean variable, whether it's produced by lab or produced by nature. So that's another Boolean value. And then there's a big union from here up to here as HR field. And this HR field actually have two tuples. Actually have two tuples to share one memory space. One is natural information, one is a double of lifetime. So double of the lifetime actually is 8 bytes, and natural information, including where can you find it. So only when natural occurring is true, then you will have the natural information. If it is false, then you will only have the lifetime. So lifetime is you use the half life cycle time in seconds of the most stable known isotope of the light. One element may have many isotopes. So if it is produced from the lab, some of the lifetimes could be very, very short, and some of them could be very long. So it depends. But if it is naturally produced, then we put this natural information there, including where can we find it. That's a primary commercial source, and also the prevalence. Prevalence means fraction by weight or Earth's crust. Okay. Then the unions, when stored, would be something like this. Is actually this one also in this HR textbook part. It has the figure 8.1 16. So right there, this chart actually you have the original declaration of this element over here. That's the same with the previous figure. And then when methodological value is true, then you put this source and prevalence. This one is actually has a union with the lifetime. So that's the field source. If you have a union and it is actually natural. So this true and false are the naturally produced. It's actually this naturally occurring. Use that as a flag to determine. So the boundary actually are different, but usually when this kind of structure and union can be a local variable, so you will be put into the stack. It usually can be put into the stack. So actually this double border actually is not a good thing. I would rather fill some dummy over there for in case that you need the union, just like the lifetime. I'll put some number there to make it of the same length. Since you need that anyway. So now let's look at the definition for arrays. And after the array, we will finish up to array part. So let's look at the array definition. Array are the most commonly used and important composite data type. An array have the index, and the index for some language starting from 1, some language starting from 0. So for example, for Fortran language, of an array of 10 elements, you will start from 1, ending at 10. But for C language, we're starting from 0 and end at 9. Pascal, I believe, also starting from 1 to 10. And you have this index, that's index, and then one location that you have value. So basic array is usually is a integer or counter accessible data structure. And so actually you can also think about this as there's a certain mapping between integer and the value. So sometimes I use the array as a table lookup for or a function that you have the translation from one function to the other. For example, sometimes if I use an array to have all the alphabet, I use the numerical number, say the character value minus the A value, that will give you the index for each of the alphabet, and we store the alphabet's value over there. That's one way to use array. So on that record, you group up relative field of disparate types. Arrays are usually homogeneous. Can it be heterogeneous? Yes, and actually, usually that is storing objects, and those objects actually sometimes they are actually under certain parent class. So it actually don't call it heterogeneous, but they was call it polymorphism. And to me, for real application, that is one way to make it heterogeneously. So you can have one upper class or interface so that you put the array of object of different type of object together into an array. And that all depends on how you use the array. Semantically, they can be thought of as a mapping from an index type to a component or element type. A slice or section in a rectangular portion of an array. We will see that later in 8.5 figure. And beyond array, we can have the associated array. we have associate memory. So one key, one value. That's called associate memory. This type of associate memory, you can use two-tuple array. So you have the key array and one value array, and you group them together. Or you have an array. Each one has a structure of key and value combination. That's also possible. And there are several ways of building up the associate arrays. And the popular associate arrays, including Python's dictionary, you have key and the value, and they put into something like a list, but they call it dictionary. Hash table in Java is also one way to organize as one way of the organization for dictionary-like data. And hash table in many data structure, it can be used as a hash value and content. But content right here, sometimes it can be a linked list. So you can have many linked lists. So if you use the linked list for the content of value, you put the linked list, then you can have multiple objects being linked into the same associate array. And we can have the SQL table in database applications. So these are the extension for array. We call it associate array or associative array. And some array is so big, and it's actually most of the entry doesn't contain the data. In that case, we can use sparse matrix. C constructed by array and nodes. So basically, you use the row pointer and the column pointer to point into the existing nodes that has value. I sometimes call it islands. So this is like an island. So each island has the row number, column number. Row is 1, column is 4, and then its value and its right neighbor, and its bottom neighbor. And anything without a node has a default value of 0. So when we access this to get a value, we just check if the object there. If not, then we will return 0, something like that. If the object exists, then we return the value. That's the way to access the sparse matrix. Array declaration. An array can declare in C language, you have the type name for the element, and then you have upper, that's the array name, and put 26 for the number of elements in the array. In Fortran, we have a character and put in dimension, the index value from 1 to 26, and then you put a upper as the array name. And Fortran also has a shorthand notation of this. In Ada, you have to put array and the range over here. So index in C, the lower bound of the index range is always 0. The index of a n element array will be 0 to n minus 1. In Fortran, the lower bound of the index range is 1 by default. Multiple dimension array. In Ada, you have array and 2 range for the 2D arrays. Fortran, you put 2 dimension number over here, and the array name is over here. We call it matrix. Modular 2D is similar to Ada, actually. It can be 2D, 2 range type declaration, or it can be array of array definition for the 2D. We will discuss this array of array things later. Okay, let's move on. And in C, C++, Java, or C#, the C family actually is using the array of array definition for 2D array. So let's look at this array of array things now. First, let's look at this show jacket array. So we have a jacket array. It's declared as a 2D, 2 dimension, but only the first dimension has the number of rows specified. Second dimension has no specification. So we create an array of 5 elements. Each element is the integer bracket type, and integer bracket type means it is a pointer to an array. So this actually create 5 tuples, and each one is one array element, but that array is only a pointer. So one on each index of jacket array, another array reference is stored. So the array reference is stored. And if we declare a array of the new integer 3, 4, the number of rows is 3, and number of column is 4, and then we try to store such a table. So row 1 has 1, 0, 12, minus 1. And then when we declare this, A will be a pointer to a 3-element array of integer. And they mark 3 as the number of elements, and each one is a pointer to another array. For example, the A0 pointing to this row 1, and row 1 has 4 elements, and the 4 elements 1, 0, 12, minus 1. So this is the array type of declaration or definition for 2D metric. Now let's look at the array part 2. Arrays in C family. This part 2, we actually focus on the array allocation and ages calculation. So if we have a type T, say character, say, and we have the array name A and number of element N, so we declare, so if T is a type and we have a character, for example, and then we have 5 elements, we will declare an A array of 5 elements, and A actually is of character type. I'm sorry, A's element actually of character type. So the total space needed to allocate such an array is N element times size of T. T is the type. So a string of 12 elements. This string is not data type. This string is the array name. A string array of 12 element of character that actually will take up 12 bytes. So initial address will be X, the ending address will be 12. And for this example, value of 5 element integer array value of 5 element will take up 4 by 5, that's 20 spaces. Double will take up 8 by 3, and pointer in 32-bit architecture, each pointer would take up 4 bytes. So in 32-bit architecture, it actually needs 12 bytes to store 3 pointer of characters, 3 character pointers. I'm sorry. And in 64-bit, actually it's 8 by 3, it will 24 bytes needed to store this 3 pointer to characters. So here is the basic principle. So this is again showing you how to calculate the size of this value array. So right here, let's read this. Value of 4. This 4 is the index 4. That value will return 5. It's an integer type. Value itself is a pointer to integer. So when you use a value of integer, you evaluate val, that will give you the ages of the starting ages for array that will return X. Value plus 1, that is of integer type, so it's plus 1 actually will return you X plus 4. So this one actually is the same as asking for the ages of, say, if we have the value plus 2, that will be equivalent to this ages value. The index 2's location will be equivalent to this val plus 2. it will both return x plus a. So these are two ways of showing the ages for a certain element in the array. So val of the fifth element is no declaration. The reason why we put the question mark here is unsure, because C language actually it doesn't check the boundary that strictly. Some compiler do check, some doesn't. So it is actually unknown here. It can return you some value, but it also can create trouble. And this body of value plus 1 would be the this location you will return 8. So this one is equivalent to val of 1 when index equals 1, the same as that. Val plus I will be i's elements ages. So it will be x plus 4i. 4i is 4 times 9. And right here, we have a type definition of integer as array, zip code for 5 integer elements. So CMU school is the zip code is 15213. U of Washington is 98185, 98195. UC Berkeley is 94720. Okay, so they will be stored each one as a 20 bytes array, and each element has an integer of 5 bytes. So declaration of the zip code digital of University of Washington is equivalent to declare integer of UW5. Equivalent array were allocated in successive 20 byte blocks. And to access it, actually, you need to, you can get digit, and then you put in the array, zip digit, that's the array, and then the index to access, and you will return it. And in IA32, you will first load the zip code ages to EDX1 register, and load the index number to EAX. So that actually will be this number times 4. You will move this indirect hexadecimal of this plus this times 4, each stepping of 4 into this register. So this is one instruction to access this array and return the value back to this register. Referencing example, this is the school zip code example. So if we have a UW3, UW of 0, 1, 2, 3, that will give you 9. UW of 6, 0, 1, 2, 3, 4, 5, 6, it will give you 4. But there is no guarantee because it's out of bound. It depends on the compiler. UW of minus 1, UW of 0 here, minus 1 will give you 3. Again, this is no guarantee. CMU of 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, I'm sorry. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 14. 15 is out of bound. Out of bound, it may return you value, may not return you value. So there's no guarantee, but we put the question mark here. So for C language, they may be or maybe not no boundary checking, depending on the installation of the compiler. Our range behavior is implementation dependent. No guaranteed relative allocation of different arrays. So index of star and edges are just a way to calculate the reference edges. And for C double plus, this brackets are operators, but in C#, actually it is not. So in C#, if it is not, you need to have special way of doing the calculation. And I leave this for you to study. And for array, you can slice or section. A slice or section in the rectangular portion of an array. Function 90 and the single array slice operation assignment. C provides extensive facility for slicing, as do in many scripting language. Let's look at this example. If we want to access this block, because this is written in function 90, so it's actually column major. So since it's column major, we try to access column 3 to 6. So it's 1, 2, 3, 3, 4, 5, 6. And row is 4 to 7. So it's the row 1, 2, 3, 4. So this is how they access this block. And each of the slice and section will have different way to access it. You can study it. Number 3, call stack or heap. Right here, I'm going to talk about the array, part 3, and actually is related to the memory model. So let's look at this. It's actually talking about the memory model. About the memory model, we have the dimension, bounds, and allocations. And allocation means we have size, scope, memory allocation. So arrays can have of different type. You have global, lifetime, static shape. The shape, actually, we talk about the dimension and size. If the shape of an array is known at the compile time, so why we may or may not know at the compile time is because sometimes the array declaration need a parameter to define its number of element, and that parameter has not been calculated, then you cannot determine the shape of that array at the compile time. But if you can determine at the compile time and they exist throughout the whole program, then it's a global array, then the compiler can allocate space for the array in static global memory. So in this case, it will be stored in the static global memory. And lifetime, local lifetime, for example, you have the array that defined in a function by static shape, but the array size had already been determined. So the shape is determined, but an array should not exist throughout the execution of program, so they won't be put into the static global memory. Instead, they will be put into the stack of the subroutine or the function. So it's actually in the code frame at runtime. And then the third one is local lifetime, shape bound at a operation time. So it's only when you execute a code, you have the definition, then you know about the shape. This is the third type. So for different language, we have support different arrays. Let's look at the global lifetime static shape. So the global variable array, we have Pascal and C global that was supported. Local time static shape in functions, we have Pascal C local was supported. Lifetime, local time shape bound at elaboration time, that's like Ada locals. Java array would be arbitrary lifetime shape bounded at elaboration time. Java's arrays actually treated like objects, so they are all in heaps. So actually, any lifetime, global or local, it doesn't matter. And for this language, they have arbitrary lifetime, dynamic shape. And I'm not going to discuss this. This is not that important. Dot vector. What is dot vector? Dot vector is a descriptor. Dot vector used to hold shape information at runtime. So because some array, their size cannot be determined at runtime, so we will need the descriptor in the code frame to determine where can we calculate the offset, so for certain value, for certain data. So dot vector or descriptor are required when the array bounds are not known at compile time. A dot vector is usually stored next to the pointer to data, So it's local to the coefficient, and actually the data can be growing. So you use that to find out where they are. Typically, a dot vector for an array of dynamic scope will contain lower bound for each dimension and the size of the every dimension. The upper bound are also needed to support dynamic outer bound checking. So it would look like this. You have all of the lower bound, upper bound for each of the array elements. So right here, if it is a constant value or static value, in Java language, we will put into the method area. And if it is not, then those local variables will put here. And for array, actually, the array, if you declare it as a static array, then you will be put in the method area for the reference part. But the body will still always be put into the heaps. So in Java, all of the array body is in heap. And the reference can be in the method area for static constant array. But for normal array, it will be put into the call stack. In C language instead, the data can be stored in the call stack or in heap area. That depends on whether it's global or local. Or actually, it's not in heap area. For those global ones, it's stored in the global data field. So the array's body for C language, it can exist in coefficient or the global static memory. And this chart is the array for Java. So for Java, if you have stored a reference in stack, that's non-static. But the string array will be put into heap. Employee object array will be also put into heap. So heap are used to store either object or array or strings. But that's not the case for C. And right here, let's look at the array stack allocation. So right here, we have a local array, 2D array, and a parameter 2D array. But this parameter 2D array size has to depending on the n that's only known at the runtime. And actually, this array this operation square trying to have one array multiplied by its own transpose matrix. So it's actually the square of its product. Actually, it's its product, but it's a square of its absolute value. So the T will hold the products, and then we copy T back to M, but M size is not known. So how can we allocate for this stack, for this array? We basically need to put that dot vector over here. So dot vector tell you where to calculate the offset and whether it's inbound or outbound, outer bound for the M memory, for the M array. And the M array is on top of the code frame, the fixed size code frame. So it won't affect other data in the code frame. And it can be growing or because their size are different depending on the runtime N. So this is implemented starting from C99. And for C++, if we have an array, we declare integer myArray5, it would allocate 5 integer in your stack for myArray. But if you have a body of the P array, the pointer to array, as integer type, we allocate 5 integer memory and then assign the starting address to this pointer. Then the data will be stored in the heap. And if you have a global static integer array, that will be stored in the global area. So 3 areas are stored for different things. And right here, we have another example of the double data type myArray that will be stored in heap. With the reference data type, the use of pointer, actually we can use more of the heap. So heap allocation, arrays that change shape at arbitrary time are sometimes said to be fully dynamic because change in size does not generally occur in FIFO order, first in, first out order. State allocation will not suffice. Fully dynamic array must be allocated in the heap. So that's what we say here. Several languages, including Snowball, Icon, and all scripting language allow strings, array of characters, to change size after elaboration. And Java and C# provide similar capability. So actually, for Java, this is not changing the content. It's actually just creating a new string to the same pointer. Java string is immutable. So top vector must generally be placed at the beginning of the heap block instead. And dynamic resizable array appear in this language, usually is a scripting language or functional language. And they are supported by vector, and vector arrays class of C++ plus Java or C# will support that. Now let's look at the calculation of the address again for multiple dimension one, more complicated one. And in array, we have using the contiguous element. For function, it uses column major and functions index starting from 1 to n. And usually people use row major, and actually it's used for any of the other language. And it is starting from 0 to n-1, and then it's row major. So this, to make this, sometimes it's the same as array of AB of array of CD. It's the same for this 2D array. So here is the column major and the row major. I talked about this before. An array, there are two layout strategy, either contiguous element. The other one is use pointer to array. Pointer to array, sometimes we call it pointer row pointer because it is row. It is actually a array of array. So, but it's row major, so we call it row pointers. So row pointer is a pointer to a row array. Row pointer is an option in C. Allow row to be put anywhere. Nice for big arrays on machine with segmentation problem. Avoid multiplication. The multiplication here actually means for the address calculation. Nice for matrix whose rows are of different lengths and require extra space for pointers. And right here, I'll show you two different things. On the left-hand side, it's called an array of character arrays. Array of character, this base is array, and this array of character array. And this day array has no specific dimension, and the character array is of 10 elements. So this day's array of character array is of flexible tuples, elements, and you just put the data in there. So, but each of the character array is of 10 elements. So, but the last one need to store \0, marking the end of the string. So actually, the longest possible string to be stored on such a 10-element array would be 9. So this is how they are. So apparently such a table has some hole. And another way is actually using the pointer to arrays. Array of pointers. So this is actually declaring an array of pointers. How many array is determined by these different strings. And each one is an array. Each one is a pointer. And this pointer has 7 array. Each one is a pointer, and each pointer pointing to a string. And that string actually stored here, it's actually in contiguous memory. So this was safe memory compared to this. Now let's look at example 8.25 for indexing to a 3D array. So if we have an array of array, we have lower bound L1, the index lower bound 1, index upper bound U1, and array second dimension lower bound 2, upper bound 2, and array lower bound 3 and upper bound 3. Then we can determine the difference. The dimension 1 is U1 minus L1 plus 1. This is the total number of elements in the array, first level array. And the second level array is U2 minus L2 plus 1. That's the dimension 2. And then we have a dimension 3. And then as size 3 is the size of the element. Each element is size 3. Size 2 is the number of elements in dimension 3 times size 3, the element. So it's the array of the elements is size 2. And then we calculated size 2. And then we calculate the dimension 2 times size 2, that give you the size of the array of L1 and U1. That's the size of each element in such a tabular array. So this array of 3 dimensions can be drawn down like this chart. It shows you which part is considered and where is L1, L2, and L3. And to calculate that, we need to prepare the D1, D2, D3, and the L1, L2, S1, S2, S3. And we calculate this S1, S2, S3, and D1, D2, D3. We use that actually to come out with the address of an element ijk in the A array. For 3D array, it would be like this. And we use this formula to calculate each individual address, each individual element in A array's address. And there is a constant that can be determined at the compile time, and the rest of it will be determined at runtime. We use the address of A with the difference from A of this element and A of 0, 0, 0. And the calculation of the address for this 3D array, when we put it into the assembly code, it will be something like this. And actually, this whole thing is trying to load the value from this element to the register. And you can study it by yourself. It's not hard, just as assembly. Okay, this session will stop here. It takes us 1 hour 46 minutes. And for the rest of it, we will break down to the part 2. And I will try to record it on tomorrow morning, 9 o'clock. Okay, thank you. Bye.